All right, so let's take another look at a simulation type model here. I'm going to pull up that, let's load the RGL library, and I'm going to simulate some uniforms, 120 uniform variables between 8 and 39. Okay, put those in X, and I'm going to simulate, I'm going to let Y actually be a function of X, but introduce some random errors there. So if you forget about this R norm stuff here and just look at this, it's Y equals 3X plus 16. Okay, but I'm actually going to tack on some error stuff there. If I didn't, then if I plot Y versus X, it'll look like that, right? Nice straight line. But on the other hand, if I tack on the random errors there, actually let me use the Windows command so that we can compare. And okay, now let's, there we go. This is what I get if I introduce some random errors off that line, right? Here's the perfect functional relationship between Y and X, but this is what you might see in real life. It's like I've taken each one of these data points and perturbed it in the up or down direction by some amount that is a normally distributed variable with mean 0 and standard deviation of 34. Okay, you can see that 34 is well, yeah, so there you go. Now when you do this simulation, your graphs won't look exactly like mine. The spacings will be different, the random point patterns will be a little bit different, and that's just because our programs are probably starting with different seeds. Okay, so let's center these X and Y values, and you can do that just by subtracting the mean off of each one. And now if I plot the centered centered Y's versus the centered X's, guess what I get? I get the same thing as I had before. Same thing, centered Y's versus centered X's, except that they're centered at 0. It's the same exact point pattern as we saw before, except it's just the new center of mass is right here at 0, 0. This is the place where it's sort of the gravitational center of this clustering. Okay. Now let's get a new window, and well, no, let's I'll tell you what. Let's do this. Let's introduce a third variable. We'll call it Z real. Z is going to be some constant plus some other constant times our centered X value squared minus some constant times our centered Y value squared, plus we'll have an interaction term now. Okay, so I'll press enter there, and I've loaded the RGL library so I can do 3D plots, and I want to I'm going to make a 3D plot of X, Y, and Z real. Okay, and I'll color the dots blue, and I'll give this thing a main title called True Functional Relationship. I didn't. You can see what happens if you don't set up this plot window like some kind of a grid where you have how we use that matrix command previously, and so we had the title and another cell sort of in this plot. You can see what's going on now. I've got the title, and the title sort of rotates as you rotate the cube around, and it's kind of annoying. It gets all in the middle of things, but at any rate, this is okay. So you can see that even though my Y values were random functions of the X value, the Z variable now is a perfect function of the X and Y variables, right? You can see how it sort of sketches out this nice surface here. It looks like this surface sort of looks like a saddle, right? And in fact, you'd probably call this point right up in here a saddle point. It's like sort of where, if this was a saddle, it's point where your butt would meet the seat. Okay, so that's sort of what's going on here. Now that's sort of it's sort of sketching out a perfect model, sort of a functional relationship there. Now let's open another window and we'll create we'll simulate some normal error terms there. And I'll just call them errors. And now what I'll do is I'll set my z numbers equal to z real plus 6,000 times the errors. Okay, that is, I'm going to jump off in the up-down direction, in the z direction, some number times the errors. And I've arrived at this 6,000 number just by playing with it. Okay, I know that that's going to give me a plot that I think is going to be good for illustrative purposes, and I'm going to plot now x, y, and z, and you'll see that in fact, okay, the z values there are it's no longer this perfect relationship, right? You can see that saddle figure is still sort of there, but it's sort of not as in focus as the other plot, right? Which was here. Blue ones are original, sort of perfect functional sketch, right? The red one is what you would get if you perturbed those blue dots a little bit in the up-down direction. Okay, so we've got some errors there. Let's do a linear model. X on that second plot there, on the modeling z as a function of x and y. And we'll do the summary of our linear model and see what we get here. So this is just like a planar model. Okay, so this is our coefficient of the this is our intercept term. These are the coefficients on our x and y variables. Look at our p-values. Only this one seems like it might be somewhat significant. Okay, this the coefficient on our y variable. What if we introduced a quadratic model? Okay, and again, to do a quadratic model, if I want to model z as a function of x squared and y squared, I use the I of x squared and I of y squared. Okay, and if I do summary of that quad model, is what I've called it, you'll see that it okay, so it looks like this y squared term is actually significant and these other two are not. Okay, I know though that from looking at the graph, however, that this is probably, that a planar model and a purely quadratic model is probably insignificant. And now remember, in reality, you would have data like this. You wouldn't have, this is the true relationship of, that models the mean response. You wouldn't really have this, the blue one in reality if you're dealing with statistics. You would have data that, maybe comes to you that looks sort of like this right here. Okay. Okay. So now let's build a model with interaction terms. And you can do that by, whoops, let me do that one more time. That was a little bit quick. Just copying and pasting from the notes. So I'll call this quad int mod for quadratic and interaction model. And I'm doing a linear model. Remember, it's linear in the coefficients. That's why it's still called a linear model. Z versus x squared terms plus, I'm going to want to include y squared terms and also interaction terms. When you do this, it will also automatically include the x and y variables themselves. So I'll do that and do summary of that, and I can see that now in fact it looks like these terms are actually significant. The x squared term that is significant, the y squared term is significant, the x term is significant, and the y term is significant. The x this, by the way, is shorthand for the interaction term. Okay, so that if I wanted to include x times y as a factor, then this would be my estimate. But the p-value is not so small there. It's at 0.0599. Okay, so maybe we could leave that out. Now I know though that in fact there was an x times y uh, term in my model. So so what gives? Well, sometimes that's what you see. Just because you know that even if you knew that things are behaving a certain way, when you build a model, it may be that that your p-values over here don't seem to indicate that you need to use all the terms to adequately reproduce the response. Our multiple r squared value, or r squared value for us, is close to 90%, so that's real good. Okay, so now let's do this using matrices. Now to do this, I'm going to want to get a column of ones, right? So I'll use that ones. I'll use that rep command. I get 120 ones, and I want to get some x squared values, right? I'll store those in xsq, and some y squared values. I'll store the squares of my y values in ysq. Okay. Remember what these operations do. They don't dot the vectors. Remember, x and y, or you can think of those as vectors or columns, right? Or column arrays of numbers. When you do this, you're squaring them element by element. Okay. And finally, I'll find xy to be the element-wise product of x and y. Okay. And then now what I'm going to do for my data matrix x, I'm going to c-bind ones along with the x values, and then the y values, and then my x sq, and my y square, and my xy. Okay, and you can check that out, see what the head of that looks like. And in fact, so here we go. This is my data matrix, right? And now finally, I'm going to use that x transpose x quantity inverse times x transpose times y formula to get my coefficients. B is the inverse of, right, transpose of x times x, and then all that stuff times the transpose of x, and then times z in this case, right? Z is the predictor there. And so if I take a look at what B is, okay, good. So this gets me exactly the same stuff, right? Here's my intercept coefficient, 5146.829 something, 5146.829 something, right? The coefficient on my x squared term was 83.9370. 83.9370. Okay. The coefficient on my xy term, 4.680261. 168. Okay, so it's right there. So you can see that you get exactly the coefficients like you're supposed to. Also, you could, if you like, you could maybe we'll plot our model here. And again, when you plot your model, it will be different from the actual theoretical, the way it looks from this. Well, where is it? Our blue plot. Remember, our blue plot was sort of our taken to be our actual mean response, what is actually the case. But when you build a model, you build the model off of this fuzzy, nasty, weird, strange data set, right? And so when I build the model, it should still kind of have this nice saddle sort of shape to it, but it won't be exactly this. And in fact, you can see that if I look at these coefficients here, they are not the same as the coefficients in my original model, which is my my z, what was it 50, something like that, the intercept term was 50. Here it's 5146 or something. Okay, the original coefficient on my x squared values was 78.6, and now it's 83.9370. Okay, you can see that these numbers are indeed different. I could I'm going to lift this. I guess what I could do is I could actually take a look. I could plot that our model here. I'll do F1 is okay. Sorry about that. Ignore this stuff right up in here. Take a look at this. For whatever reason, I'm calling this F1. Is going to be my intercept coefficient. All right, minus 4508.727725 times some value. I'll say A. Okay, and then plus here's my coefficient on the y's. Instead of y, I'm going to use BB. Okay, and then here I've got 83.9370 something. This number times A squared minus the next number times BB squared. Okay, and then here's my interaction term. Okay, so now if I open a plot window and execute this command here, whoops, you can see that did not work out like I thought it would. It's a plane. I've made a mistake there. Let's see if I can figure out what. You can see the problem is right here. I missed a decimal place. Okay, so look at the effect that it had when there should have been a decimal point here at between the 8 and the 7. So this slope, if you will, is humongous. It's sort of dwarfing all the other effects here, and so of course you're going to see a plane. It's going to all these other effects are sort of negligible with respect to this one, so I think that's why you're seeing it flatten out. Let's try this again. So if I go up here to F1 like so and enter that decimal point, okay, and like so and like so, and then there we go. All right, now you can see this is my nice model. I've colored it like a rainbow because that's fun, and notice though that this is a little bit different in several ways. One way that it's probably kind of difficult to tell is that it doesn't it's not it doesn't line up exactly on. It's not the same surface as the one that's sketched out by the blue points here. Okay, and that's because this is sort of the real surface. This is the estimated surface based off of our data. Also, in the real scenario, take a look at what happens if you look at this from the top down. This is our original XY scatter plot. That is, if you drop all the points down to the XY plane, you should see this kind of thing. And you didn't have any observations over here or over here. However, in this case, I've simulated uniform random variables in both directions, completely uniformly across this square. So you see it's more filled out. Okay, and this would sort of our model can be used to predict observations or mean response for other XY values that are even outside of where we made our original XY observations. Okay, so there's that. Also, it's just kind of cool.